The product of interest in this series of lectures is Connected Components Workbench. And we'll refer to it as CCW because it takes too long to say Connected Components Workbench every time you want to refer to it. In particular, this series of lectures supports this manual. Now notice I said this. This was one document of too many pages, spiral bound. It became too cumbersome for the learner to handle, so we broke it into two documents. This series of lectures will discuss the contents of these two manuals, but it won't cover everything in these two manuals simply because we're assuming you have these manuals in front of you and you are going along with us doing these projects. It's all hands-on learning, doing these projects with a Micro800 controller. Now you can do it with a Micro810, but I don't recommend that. The price of a Micro810, by the time you've added on the USB communications adapter, you're at least at $120 or so. And if you add the little display that plugs in the front of it, you're well over $150, $160. A Micro820 is a much better approach using the HMI. An 810 has USB DF1 and that's it. And it's fairly easy to use. An 820 has Ethernet. Ethernet is definitely the way to go. The 830 does not have Ethernet, so the next step up from that is the 850. Now you're talking a lot more money, and the 870 even more money beyond that. So the 820 with a little remote LCD screen keeps you under $500. And of course there's also a matter of Connected Components Workbench software. Right now the current release is 11. By the time you watch this video it might be 12. But with release 11 they also came out with something called the feature pack. And the feature pack has some really nice features that it adds to the software. Another consideration is the developer edition of this software, CCW. Without the developer edition, you're missing some really handy features. And I don't know what the developer edition costs. Call your local AB distributor, Rockwell Automation distributor, and ask them for the price on the developer edition. A Micro820 with the remote LCD and the developer edition is the way to go. And definitely download the feature pack. We'll be using that. The main point is you can learn a lot by watching these videos without buying the manual. I record these lectures looking at the manual and not going over what I see in the manual except the results of the lab projects. I don't discuss any of the technology, any of the go asides to discuss how things work and why they function the way they do. So I strongly encourage you to get a copy of this manual if you can. Even if you want to share it with a friend or a group of friends and take turns using it, get a copy of the manual. These lab projects build one on another. If you haven't done the project before this one's going to make less sense than if you had done the previous lab project. In this next lab project, we're going to start using module-defined tags instead of tags that you defined. In the logic before you, you see bit 1 through bit 5. These are Boolean type tags that we created. We typed in the name bit 1 through 5 and we define it as a Boolean data type. We're going to enhance that understanding a little bit. I had you double click on bit 1 to bring it up and then add a 6 to it. So now it's bit 16. We added a 6 to bit 1 and the text says bit 16. But you notice the yellow triangle, warning triangle with an exclamation mark. And of course we know that means that there's something amiss with either the instruction or the tag. And of course there's nothing wrong with the instruction, so it's the tag. Bit 16 is not a tag. If I double click on it again and backspace out the 6 and hit enter, see now it's a tag again. Connected Components Workbench recognizes bit 1 as a defined tag, but not bit 16. And if I mouse over bit 16, it says name bit 16. If I mouse over bit 4, it says name bit 4 type Boolean. So you see the type is missing from this one. The difference here is that bit 4 is a tag, bit 16 is not. Then I had you right click on bit 16, bring up variable selector, and notice that it pops up ready for you to define bit 16. So bit 16 is already in, so it's somewhat intuitive, and because of the type of the instruction, it assumes it's probably Boolean, and the local scope is program 1. However, we don't want you to define this as a local scope for program 1. We want this to be an I/O tag. So we go to the Micro tab, I/O. In the manual, it shows Micro810 for this tab. Well, this tab is going to reflect whatever processor that you're using. I'm using an 820. So we click on that tab, and it brings up all of the tags that we have available for I/O. And because this is an 820, it has 20 total I/O inputs and outputs. So you see there, digital input 0 through 11, that's 12 inputs. Then you also see 0 through 6 outputs. So that's 7 outputs. Now remember, this also has a output, and it also, you can use the first 4 inputs as analog. But you notice that they're not shown here. Notice that this is digital input DI and DO. And that's everything you've got. So that means that this menu now, or I should say this pop-up under the tab, is context sensitive because it's not showing you what you can't use. It's only showing you the digital I/O. Then I had you select digital input 0 and OK. At this point I had you download it, so we've changed one of these tags to an actual I/O tag. Now remember that this memory location, this name was predefined for you as a module defined tag. This tag right here can only be controlled by the input attached to the screw terminals on the controller for input 0. Let's download. I'm going to pause while we wait. In the manual, I show you a message that can pop up that says connection failed. That is exactly what happened to me on this particular download because I let this system set overnight running. When the computer went into screensaver, evidently that dropped RS Link's USB connection. When I tried to download, it came up and said connection lost. And just as I told you in the manual, I said if it does, then just retry it and then select your controller, and that's what I've done. Download, I'll pause again, and voila. We're downloaded. The first rung is false, the second rung is true. Now the first rung would be false if either of those 2 instructions was false. The same for the bottom rung. So both rungs would have to have both of their instructions true to be true because these instructions are ANDed. So you have to have digital input 0 on and bit 4 on to turn on bit 2. Bit 1 has to be off and bit 5 has to be off to turn on bit 3. Now we're making a transition here from working with bits in memory that have no external influence other than from your keyboard and mouse or maybe from an HMI, but definitely not from the voltage levels on the input terminals of the controller. So let's open up global variables and look at our inputs. Now I see that input 4 is on. I look over here and sure enough I have input 4 on. If I turn it off, you see it goes off. I had you select digital input 0, but if you remember from instructions in the manual, we are not using digital input 0, 1, 2, or 3 currently. We've wired up our digital field device simulator to 4, 5, 6, 7, 8, and 9, those 6 inputs, because we wanted to leave the screw terminals for 0, 1, 2, and 3 open in case we want to add analog inputs later on. That may cause you a little consternation, because if you have our digital field device simulator, it's marked input output 0, 1 through 5. That isn't what we're using here. But later on we will do what we call I/O mapping and buffering. So what you will be working with is something that says IN00 for input 0, but it's going to be aliased or buffered to the digital input module defined tag IO embedded DI04. Now we did this just for convenience, and if you hang in there, you won't stay confused if you're confused now. What I did want to show you though is that I'm going to turn on input 4, 5, 6, 7, 8, and 9. The 6 toggle switches on my digital field device simulator, but because I have them wired up to 4 through 9, that's what's coming on in my data table. Nothing is connected to 0 through 3. Those screw terminals are empty. I'm going to go back to the program, and I'm going to change this to 4, digital input 4, and then come back. I changed the tag addressed by that very first true if on instruction to be digital input 4, which is connected electrically to my digital input 0. Now this should not confuse you. In your manual it shows digital input 0, 0. I have to assume that you probably have an Micro810, which has 6 inputs and 4 outputs, and although some can be used as analog, there's not enough I/O available on the 810 to accommodate everything we want to do in our labs with the 6 digital inputs and accommodate some analog inputs. So we're going to kind of go back and forth here. In order to do the live lab screen captures, I'm going to have to use digital input 4 instead of digital input 0. Later on I'll show you how to get by all that by I/O mapping, where you create a tag IN00 and you either make it an alias for input 4. In other words, it says input 0, but it's alias to the actual digital input 4, or you use something called buffering and you still come up with something that says input 0, but it's really input 4. You have to get used to the idea that there are a lot of I/O points out there to use, and when we have something like an 810, we're very limited to 6 in and 4 out. But as we use controllers that have more I/O, we have a little bit more latitude. Just keep in mind that I have digital input 4 attached to the actual toggle switch on my digital field device simulator that's marked 0. It's just a switch. It controls voltage to a screw terminal. Instead of using 0 through 5, I'm using 4 through 9. One thing I want to make sure that you understand is that if I have these input screw terminals 4 through 9 with a high voltage level, and I'll start turning them off here, they're all off now. If I go back to my program file, so the only thing that can control the state of that bit is whatever's attached to that screw terminal. I can right click on it and toggle it, and you see it change, but it goes right back. So it is reflecting that it was changed, but because the scan rate updates the input image every program scan, and I toggle this on at the end of the scan, it's on or off, whichever way I toggled it. And then after you get done doing the output update and the input update during the input update, it's going to overwrite whatever I put in there with whatever the screw terminal actually is. That's what we're emphasizing in this particular lab project on using I/O tags. That, unlike the bit 1, 2, 3, 4, and 5, those were internal tags, if you want to call them that. Now remember, they're all memory locations. This is a memory location and in every way equal to any of these other memory locations. The only difference is what externally to the controller can effect a change in the state of that bit or has influence over the state of that bit. In the case of bit 1, 2, 3, 4, and 5, if I toggle that from the keyboard, it stays. I am the only influence over the state of that bit. If I toggle this one on, it goes on for a partial scan and right back off because the voltage level on the screw terminal, in this case screw terminal 4, input 4, it has the last say on the state of that bit. That is the main thing that we're emphasizing in this lab, is that relationship between what I call internal tags and external tags. The only variation that I have here between what you're looking at on the screen and what you see in the manual is instead of 0, 1, and 2, I have 4, 5, and 6. They're still sequential, and they are connected up to the first 3 inputs on the digital field device simulator. Then I had you download the project and go online. We also did something different in that we are reading an output bit as a condition in a rung. So in the first rung, 4 and 5 have to be on. So I'll turn on 4, turn on 5, and now you see the rung is true, and it turns on I/O embedded digital output 0, 0. Now, although I have my input shifted 4 points to accommodate the possibility of using analog 0 through 3, my outputs are 0 through 6. Notice that when rung 1 went true, rung 2 went false because we are reading the state of that digital output as a condition in rung 2. So in other words, if inputs 4 and 5 are on, there's no way that bit 3 can ever be on, because a condition for bit 3 to be on is that you would have to turn off digital output 0. And what influences digital output 0 is the state of digital input 4 and digital input 5. Now in your manual it would be 0 and 1, not 4 and 5. But you understand. And actually the mental gymnastics that you're going to have to go through to associate 4, 5, and 6 with 0, 1, and 2 is really good for your understanding of the data table and the relationship between module-defined tags and just plain old ordinary Boolean-defined tags with no other external influences. The only thing unique about the I/O tags, if you want to call them that, is that electronically and firmware-wise, because electronically the voltage level at terminals 0 through 11, those 12 inputs, are going to be felt on those 12 bits in memory. Every time the program scans, it's going to take the state of the voltage level on terminals 0 through 11, input 0 through 11, and it's going to set those bits in memory equal to that state, on or off. The outputs are not quite as locked as the inputs. The inputs, if you're in the run mode, no matter what, the state of those 12 bits, and this would be true of all PLCs. If you're in the run mode, all of those module-defined tags that are associated with the input electronics, they are controlled 100% by the state of the screw terminals on that controller, even though you can toggle them momentarily from the keyboard. The output screw terminals, however, are controlled strictly by the state of those bits in memory. And if there's no logic to turn them on and off, then they're not going to change state unless you go in and toggle them on or off. Now this one is off. Watch what happens when I toggle it on. I watched my digital input simulator and that output never came on, even though you see it flash red there, and that's the software responding saying, yes, I see that you toggled it on. And then immediately when you scan this rung of logic, rung 1, this has a false rung out, which means the whole rung's going to be false because they're ANDed. Now if I ORed them, in other words I put these two in parallel, then either one or both would control the state of that bit. In the manual, I talked quite a bit about the rung zone markers. If you refer to roughly page 79 in the manual, and remember that can change. So it's at the end of this lab where it says save and disconnect. Then we're going to start talking about buffering I/O because that's very important at this point. So we can kind of get away from this, well, Tim, you shifted 0, 1, and 2 to 4, 5, and 6, and that doesn't match my book. So we're going to get away from that a little bit in the next lab. But between this lab and the next lab, we have a discussion on rung zone markers and why buffer I/O. You need to read that section and then do the next lab and we'll come back to you. One more thing. You need to start thinking in terms logically of what controls the write instructions at the end of each rung. In rung 1, inputs 4 and 5 have to be on for digital output 0 to be on. If either 4 or 5 is off, then digital output 0 is off. Now bit 3, when you look at the conditions there, it says digital output 0 off and digital input 6 off. However, because digital output 0 is not controlled externally but by logic, you now have to consider what digital output 0 is controlled by, which it is in the first rung. So if you wanted to, if this was all the logic that there were, you could substitute those two instructions in the upper rung, rung 1, true if on, input 4, true if on, input 5. You could take and move those down and replace digital output 0. However, you would have to write logic that says if either one of them is off, then this rung would be true. So think about that. That's just something to think about. So if someone says, what controls the state of bit 3? You can't just say digital input 6 and digital output 0, because digital output 0 is controlled by the state of digital input 4 and digital input 5. So you could take and embed rung 1 into rung 2 if this is all the logic there were, but keep this in mind. You couldn't just take and, here, let me flip that back. So I've got both of them on, 4 and 5, right? Digital output 0 is on. I can't take if 4 is on and 5 is on and substitute it for the if digital output 0 is off. I have to invert the logic of 4 and 5, and that is a subject for another day. However, for the sake of troubleshooting, this is what you're going to be looking at. You might be looking to see why bit 3 is not on. So you look there and say, well, input 6 is off, that's good, but digital output 0 is on, so this true if off is not true. Now, let's say there were 200 rungs of program, 200 rungs in your program. You'd have to go find that upper rung, wherever it is, and then look at it and say, okay, digital output 0 is on because 4 and 5 are both on. So you would either have to turn off 4 to get bit 3, or you'd have to turn off 5 to get bit 3. So you see that the results of rung 1 is absolutely part of the results of rung 2. So let's read this rung of logic here and put some words on it. In other words, if this, then that. If digital input 6 is off, and if digital input 4 is off, Or if digital input 5 is off, then turn on bit 3. The thing to notice here that this rung says if 4 and 5, then digital output 0. But it also says, inferred, if not 4 or not 5, then not output 0. And down here we need a not output 0. So we would have to invert these two instructions. They would have to be true if off, and or together if you moved them down here. Just something to think about. See you in the next lab.